So we've been exploring the following equation written in terms of the summation convention for two derivatives in both space and time, plus m squared, and we called phi 1 the solution to a delta function in space-time. So we're sort of insisting on this sort of bad notation. It's x naught, but it's a 4-vector, so we have an a there. There's a disturbance at x naught in space-time, and that disturbance spreads out in space-time, and we sort of assumed the solution, but we can think of it as right, when this is 0, the solution is just plane waves. So the solution to this disturbance is really a sum of weighted plane waves. And so we can write this in this form. Here is the plane wave e to the I k a x a minus x naught a, weighted in terms of some function of k, right? So every k has a different weight. Every plane wave with different values of k has a different weight given by this function, and we want to find g of k. So let's put this into there and see what is implied for g of k. So we do d mu plus m squared acting on phi 1, which is this. So I'm just writing this again. And it's acting only on, right, these are time and space derivatives, so here are time and space in the xa's. And so therefore we get integral d4k 2 pi to the 4th. So now we act on this. We've already seen how this works. We pull down minus ka, and then we have just m squared, or this goes along for the ride here, times the same thing. So e to the minus I ka xa minus x naught a g of k. And and we know from this that it has to be delta function, xa minus x naught a. And we know that the delta function has a representation which looks like just this part, e to the minus I ka xa minus x naught a. And therefore it follows that given that this is a representation for this, that g of k must be the inverse of this, to cancel this, minus ka plus m squared to the minus 1. And so let's sort of conclude by comparing what we had in quantum mechanics, where we got a wave function in one dimension. It's psi of x and t. It's a one-particle description, right? The probability of finding the particle at some location x at some moment in time is just psi of x and t modulo squared. So this is the amplitude for finding the particle at that location at that moment in time. And by contrast here, what we see is that psi 1 is the amplitude for a particle which makes up the field to go from a space-time point to another. So this is sort of the analog of the one particle that we have in quantum physics.